We're going to talk about Jovian Tesla radio. Now, Nikola Tesla was a great, gifted man. I don't think he made a connection to Jupiter, but by the time we finish, you may be doing some of that. My colleagues, Bogdan, Bogdan is here. Robert is around. Ken Roy, okay, Ken. Joe Teague is not here. Raj is here. So we're all kind of getting stuck into some of these projects together. But radio astronomy is actually a two-way project. And my acquaintance with it came from just a number of things, studying physics, thinking about it, and also reading the books by John Krause. He was a great, gifted teacher and radio astronomer. And he pointed out that the windows we have for studying distant things, and it's the same for anyone that lives on a planet with an ionosphere. So if we're talking about sentient, it's a two-way street. They've got their ionosphere, we have ours. So we have windows through the ionosphere. We have some windows permitted by molecular bands. We have the optical window, which we love. We have the radio window, which takes us down to the plasma cutoff frequency. That's like 5 to 10 megahertz day. It's like 2 to 5 megahertz night. And above those values, the ionosphere is reflecting, absorbing, and it has a lot of character. So, in practice, radio astronomers, this is they're not going there. This is cherry incognito. And I want to explore if that's a reasonable assumption. That's the conventional explanation. The ionosphere is more complex than the daytime when ions are formed by solar, UV light, X-rays, and so forth. More where the radiation is, more where the air molecules are, and the combination of air density and radiation gives us a complex structure. And then at night they fade out. Nighttime ionosphere is a lot more predictable, a lot more kind and forgiving. So this is pretty conventional so far. I'm about to depart from conventional radio astronomy by considering what happens if there's a magnetic field. But this is still fairly safe. This is lossy electrons, electromagnetic wave interaction, and number density of the electrons, charge on the electron, epsilon naught, and electron mass. So when one is below the Langer frequency, there is absorption. If you have a magnetic field, there's an additional interaction because the electrons get kicked around, they spiral around the magnetic field, and the cyclotron frequency is given by this equation, E over M ratio and the magnetic field strength. That's where the funny interactions come in. That's where the plasma physics comes in. And the Appleton-Hartree equation, which looks like that, tells us how the wave is transmitted. That's the index of refraction squared over there. These are parameters based on the cyclotron frequency and the Langer frequency. So you take this equation, you start plugging in things and see how it behaves. I've already simplified it because I took out some angular dependencies where the angle is the angle between the incident radiation and the magnetic field. So it's already simplified. And you start with this and say, well, what happens above that frequency? A lot of absorption. What happens below it? And it gets interesting. That's where you're interacting with a cyclic system, with the electrons spiraling around. And my analogy, classical analogy, is pushing the kid on the swing. You don't do much if you push him at too high a frequency. You don't lose energy. The kid on the swing doesn't gain energy. And push close to the resonant frequency, the amplitude of the kid goes up. It's a lossy thing still. But consider it's not a cute little kid like shown here. Consider it's a medieval kid. He's a street urchin. He's sticky. He's got apple juice, sugar, mud. And he's a real, one of those kids you don't want to touch. He's sticky. Now, if you've got this kid on the swing and you push him, you can give energy into him, but if you're not careful, you're going to get pulled along with him. You're going to actually gain energy. He's going to push you along as you interact. That's what happens below the cyclotron resonance frequency. Things get interesting. And you might enter into the extraordinary wave region, below the plasma frequency, go a little lower. Go below the cyclotron frequency. And then the index of refraction, a little bit simpler. But you can drop down to this equation. I'm choosing that one because that's where I want to go. This is the equation for right-handed circularly polarized waves. It says the electric field vector, there it is. As the wave advances, it turns this way. It's right-handed. It goes this way, as it advances, it's left-handed. Build your antennas differently, that sort of thing. So the right-handed polarized wave, circularly polarized wave, gives you that equation. And I had Excel going. I put that into Excel. It looks like this. The low frequencies, the index of refraction, took the square root of it. It's like 1.6. And then in here it goes less than 1. Less than 1 means it's lost, very lost. And there's a lot of stuff left out. Things like electron number density, all along the path is left out. This is a terrible oversimplification, but it says that low frequencies, definitely below megahertz. 1.4 megahertz is the cyclone frequency. Probably below 100 kilohertz. It may be interesting. Maybe not much absorption. And this is where the radio astronomers are no longer on the boat. So, question is, did anyone try to measure anything here? And go back to 1961, the Navy had some experiments called the lofty satellite experiments. And they saw the signal at 18 kilohertz, they did it well, they made a lot of measurements, and they said, whoa, theoretically upper bound of 2 dB absorption. That means the signal is going through the ionosphere, less than half of that signal is absorbed. And they had some results, reasonable. If you do it only at night, don't do it in the daytime. This means a lot of absorption. But basically, do it the right way, special conditions. You can have transmission through the ionosphere. And their data, pay no attention to the curve. It's daytime. This is night. The data's pretty interesting. Maybe you can hear things. Maybe you want to do radio astronomy. So this is an aside, okay? We're going to go aside. We'll come back to it. But could one hear anything? And the thing one might listen to, well, is the sun, right? That's daytime. How about Jupiter? Jupiter sometimes up at night. And the Voyager data show that there's really a lot of energy down here. Here's our 1 megahertz, 100 kilohertz. Here's what the Navy did the experiments. There's more energy per hertz, per cycle per second, to drop like that. More energy per hertz down in these low frequencies than up here, where everybody listens, everybody on the planet, dealing with the ionosphere. So it looks like to me, hey, could be reasonable. We might be able to detect signals through the ionosphere. We might be able to do radio astronomy, maybe sending. And question comes up. What are the criteria? I don't want to dwell on this, but you've got the idea so far. Nighttime, the radiation comes along the magnetic field lines. Do it at a time when the sun is quiet, things like that. Just practical stuff. Maybe we could do that. So, 2 questions. One, has anyone else done it? The Navy did some things with satellites. Has anyone ever heard Jupiter? And secondly, who was the first radio astronomer? Carl Jansky. He's got a good claim to it. But you know, maybe, what if you look at the historical literature? Here's this guy. This is Nikola Tesla. He's got, I think when he turns it on in 1898, 1899, he's probably got the only radio transmitter on Earth. And his transmitting station looks like this. And amateur radio operators get envious, and they also shudder, I guess. The point is, he was really a great man. He also listens to this thing. He turned around. He had the world's biggest antennas, as you might guess. He also had, for that time and for several years, the most sensitive receiver. And he did that with a gadget that nobody uses. It's called a coherer. And nobody uses it because it doesn't resolve the envelope of a wave. It turns on, and then you have to turn it off. But he had this, and he biased it in a very creative way. So, at that time, 1899, he reported hearing a series of clicks. You can read this. But these were clicks unlike anything he had heard. He trained himself to listen to and interpret the Earth's noise because he was interested in the ionospheric cavity, shell around the Earth. And he had some uses for it. So he said, well, This is not earthly. Mars was overhead. Mars was in the news. Claudio, you recognize the background? The Italian scientist, space scientist,
Yes, Schiaparelli.
Schiaparelli, said, look at Mars. There's life on Mars. There are canals. The canals come and go. Mars was in the news. He made these observations in 1877, published 1887. H.G. Wells was writing books, War of the Worlds, published 1889. And Tesla was immersed in this. People were saying, things are dynamic on Mars. There's probably a civilization. And Tesla jumped on it. Mars was in the sky. Mars started setting. The eclipse disappeared. So he announced this. He announced, I've heard Mars. And no one collaborated. Why? Well, no one else had a receiver. That was pretty good. But also, he was wrong. So the signals weren't from Mars. And Mars may have some signals, but not those. They're probably from Jupiter. So let me go back to this and rewrite it like this. I'm going to say Mars and Jupiter both set late in the evening. He continued his observations, which included this type of event. Now, you can go on the internet, it's easy to find, and download some software written by a friend of mine. You can predict radio storms from Jupiter. They're based on movements of the moons and the orientation of Jupiter, where the Earth is oriented, things like this. So I went through it, and other people have too, and you see that Tesla's observations include this, what we call an EOA event. It's a significantly interesting time of radio emission. So I think Tesla probably heard Jupiter. And pretty exciting, really, because he was actually using 18 kilohertz, the same frequency the Navy folks used. Now, special conditions, those conditions I mentioned before seem to have been satisfied. No QRM, that means no competing radio stations. So he had special conditions. We might not be able to do it now. But it's pretty interesting. Now, how about this weird condition that the radio waves have to come in along a magnetic field line? This is the way the magnetic field of the Earth looks, something like this, the background image. So if you take your compass outside and you use it, you're happy with it, you go to the southern hemisphere, it probably doesn't work. And, why doesn't it work? Well, they get dragged. They don't have a balanced needle. They're unbalanced intentionally for the northern hemisphere. So the southern hemisphere, you want to get a different needle. And you have to give attention to what the dip angle is. So if you've got a watch that has a compass, you can use it. If you go back to the old physics instruments and get something like this, you can use this to tell you what the dipping angle is. You line it up so it points north. You flip it over, and you read off the dipping angle. So you can also look it up on the internet. But Tesla was in a pretty good spot. Tesla was over here in Colorado Springs. And there's a significant dip there, kind of in the direction that Jupiter lies. You look it up, the inclination is 65 degrees from the vertical. So, once again, to me, it's an unused radio astronomy thing. Kind of an interesting possibility. I don't think we should ignore his prowess in technical fields. He was a very astute man. I think he was probably the first radio astronomer. Okay. Conclusion? This is the first conclusion. We can do radio astronomy and SETI from the Earth. So conclusions are fun. Let's go ahead with it. We can get speculation. Can we detect interstellar VOF signals? Well, think on it. Is there any frequency that penetrates the ionosphere that hasn't been investigated? VOF. Is there any frequency that our government spends billions on to penetrate the oceans? VOF. Is there anything that has a large skin depth so it penetrates metals, springs, Faraday cages? VOF. It's an ideal frequency for SETI. Our first conclusion is radio astronomy has been demonstrated, it has potential, it's an unexplored region for us to explore. So it's an opportunity. It has some interesting other characteristics that I just mentioned. bi-directional. Ideal for study. Anything else? Could be a robust communications channel. It could work with submerged or subterranean ET guys, or Earth colonists, or research instruments. And I think it's an interesting new approach. So, what are we doing about it? Several things. One, we're trying to build some antennas that are sensitive to left-hand circularly polarized and right-hand circularly polarized. This is a piece of one. This is the first one, and we've got plans to build 3 of them for different purposes. It's not quite complete. It needs something to do some phase shifting. So that can be either about 2.5 miles of wire. We don't want to go there. Or a little phase shifting network or some special software. But anyway, this is starting. Second thing is experimental investigation of ET signals. Well, we're going to connect this up to some computers. And we're working on that system. One of the computers is going to be a benchtop development system. It's under benchtop development. Software-defined radio for radio astronomy. Bo Don gets to wave again. He's over there. We're plugging away on that one. And the future is FTSP, which I go back and forth on FTSP. It's going forward through speedy photons. That's one thing. And the other, if you watch a lot of science fiction stuff, the other is frill the slow photons. It says you want to go faster. So this is a slide for our reactor. It's going along in several phases. And one little workshop here in Oak Ridge at the observatory, one's in Atlanta. That's another story.